Our latest result is this new work-energy relation. It's not the work-kinetic energy relationship, but it applies to systems consisting of several objects connected by forces that are considered internal, and they might be springy, so the whole object can sort of compress or expand, like the masses connected by springs, or the book and the earth connected by that springy, invisible gravitational force. And our new theorem involves this thing called the change in potential energy of the system. But we need to learn how to calculate something about the change in potential energy of the system. So how do we do this for an internal spring force or gravitational force? And the answer is, well, we're going to do it the same. The definition of the change in kinetic energy is just the negative of the net work done by internal forces. So we're going to use that. And let's do it via an example at first. Here's the case where our system consists of the book and the earth, with the gravitational force between them being considered to be an internal force. And we want to calculate the change in the potential energy as we go from that initial to the final configuration where I'm raising the book up with my hand. Okay? Let's put the internal forces, show them in here. So here's one internal force, the weight force on the book. It's the gravitational force on the book. I'll just label it as mg if the book has mass m. There's also an equal and opposite force on the earth, but I'm not going to draw it in because the earth doesn't move, and so that force isn't going to do any work on the earth. The earth, if I push the book up with my hand, the earth essentially stays stationary and the book does all the moving. So we only need to worry about the work done on the book. Things have to move, or at least the point where you're applying a force has to move if there's going to be a work done. So we don't need to consider the work done on the earth. It's essentially staying stationary in this process. Okay, I raise it up with my hand. Here's this internal force that's being applied downward. It's doing negative work the whole way up. All right, we're going to take an axis to be upwards from the earth to be plus y. So I'll call that my plus y direction, upward from earth. And let's suppose that the book starts out in an initial y-coordinate, y initial, and then a final y-coordinate, yf, final. And even though it looks like the book is being lifted a tremendous distance from Earth, I'm imagining both of these positions are very close to the surface of the Earth, so that approximation mg for the gravitational force still makes sense there. All right, by definition, the change in potential energy is the negative of the net work done by internal forces, and so that's the net work done by the gravitational force. I got to keep that minus sign coming along for the ride out in front. Here's that minus sign again, just coming along for the ride. And now I've got to calculate in the big parentheses here the work done by the gravitational force in between initial and final. That work itself in the big parentheses is negative because the gravitational force is pulling down as the book moves up. That's the hallmark of negative work. So I put another minus sign in there inside the parentheses because it's negative. And then the rest of the stuff here is just positive. Remember, when you have a constant force acting, it's just the magnitude of the force times the magnitude of the displacement is the magnitude of the work, and it's negative work in this case. Okay, so how far it was displaced was y final minus y initial. So let me just multiply all these minus signs through and simplify this mess a little bit. I get mg times y final minus mg times y initial. So notice we're saying the change in potential energy is mgy final minus mgy initial, and that seems to suggest that there's something called the gravitational potential energy, which is just mgy. So the change is just the final gravitational potential energy minus the initial gravitational potential energy. So let's put that in a list here. We're going to expand on this list a little bit. We found out that if our system consists of an object near the surface of the Earth and the Earth, with the gravitational force being internal, then the potential energy function that we should use in order to use this more general work-energy relationship is mg times y, where y is the y-coordinate of the object that's moving relative to Earth, and we always have to take plus y to be the upward direction. Otherwise, this has the wrong sign. So if we're going to use this formula for the gravitational potential energy, we have to take plus y to be up. Our goal now, well, before I say that, Uh, First of all, one thing to notice is that when an object is close to the Earth's surface, and we're considering our system to be that object plus the Earth with internal gravitational force, if we lift the object up away from the Earth, then the gravitational potential energy increases. So we're thinking of that as energy stored in the system. In the same way, when I have a moving mass, that mass is kind of storing kinetic energy in its motion. Here we're storing potential energy in a springy force, and potential energy in this particular case increases as we stretch the invisible spring that's pulling between the Earth and the object and raise it to a higher height. Similarly, if we lower the book down, we would decrease the potential energy stored in that system. The reason it's called potential energy, or at least one way you might explain that, is because it can be converted into kinetic energy by, for example, letting the book go. So if I let the book go, it starts to enter in free fall, and what was potential energy ends up being converted into real kinetic energy that I can see. The book moves faster and faster as it accelerates. So our goal now is to develop potential energy functions for two other kinds of forces, or at least two other situations, and those are the only three that we're going to use in Physics 110. So we can kind of contain what we need to know about potential energy functions. The second one, besides an object near the Earth's surface, and considering that gravitational potential energy, second one is if we have two objects connected by a spring force, and in order to develop the potential energy function for that, we need to know a little bit more about the spring force. So we'll do that in the next video. And the other case is, this one is limited to the situation where the object is very close to the surface of the Earth. What about if we have the moon and the Earth, where the moon is not near the surface of the Earth? Can we get a potential energy function for that situation? And the answer is yes. It's complicated to derive it. It would require calculus, but we'll introduce it and show how to use it in this class. So we'll do that after this break.